Is that?
Gotcha.
Okay, this was your designs. Can everybody hear me?
Yeah.
Okay, so this was, and y'all can see the PowerPoint, right?
Yes, sir.
Okay, this is photoelectric proximity sensor 3. This was our design project that we had. I think we had 8 people out of 16 that turned them in. So all the rest of y'all guys, I gave y'all, this was due the Friday before y'all got out on spring break. So it kind of concerns me that we had very few people that even gave it a shot. So this is the design project. We're just doing the basic part of a car wash system, and it's not exactly the way the car wash actually works, but it's still our design project. It says in the vehicle stop application, the following circuit design requirements needs to be met. A photoelectric switch is needed to detect when the vehicle is in place or has reached the desired location. Now, I didn't do it on this one. Over here on the left-hand side, I had some notes that said we was going to use a retroreflective sensor. Okay, so a retroreflector sensor means it's got a true output when the vehicle is not in place. And one of the problems we had is some of y'all just got out of PLCs, and some of y'all hadn't quite had motor controls yet. So these are motor control diagrams, guys. These are not PLC diagrams. These are motor control diagrams. When the vehicle says the photoelectric switch is needed to detect before the vehicle is in place, the green light, a green light should be on and a red lamp should be off. When the vehicle is in place, the red light should turn on to signal the vehicle to stop, and the green light should turn off. And then after 10 seconds, then the red light will automatically turn off and the green light turns off. And then we're going to use a programmable timer or a timer. There's just a basic difference. We need a push to test on the red light. Okay. So this is the simulation. So we're using a retroreflector up here. So it's either a through the beam or retroreflector. Retroreflector doesn't would work the same way. But what we need to understand is this guy right here gives us a true when there's no vehicle there. And then it's going to give us a false. When the vehicle comes up here and breaks the light, it's going to give us a false. So we'll start off with the green light. Being on, and the red light will be off. So this is the first design. It looks like whoever did this one just drew the way we would connect the circuit up to a PLC. And we're not using PLCs in this class. We're using relay logic. There's another problem. Can y'all see another problem? Yes, no? They're using an input hooked up to an output. It looks like this is their output side, and it looks like this is their input side. And we have our photoelectric switch hooked up to an output. So, and then you got a CR over here. So if you're doing PLCs, guys, the photoelectric cell would still be hooked up over here, and then your program would, and then the CR would be over here. This input would run through logic and control that output. But still, this is not right because this is a PLC wiring diagram, and this is not an electrical diagram, right? Okay, what's wrong with this one? Anybody see anything wrong with that one? I need accurate. Don't know this
Well, I
is,
didn't think I have a push button at the bottom.
right down here. Well, this one is okay because according to the specs, we're supposed to have a push to test for the red light. So what we're supposed to do, whoever did this was right, because what they do, and no matter what's going on here, they can do what? They can push to test the red light. So that was okay. I don't quite understand this one. So they start off okay. So this guy here's true. So this is going to be closed, right? This starts off true. So this guy will be closed and the green light will come on and the red light. I don't know. Oh, I don't know what you're doing. CR is CR. There's a, okay. So and then they don't. Then this is once again this right here is PLC logic, where we identify the timer as being we identify the type of timer. In motor controls, what we do is we identify the type of timer by the contact we use. So we have 4 contacts. We have this one. And we have this one. And then we have this one. And then we have this one. So what we do is we don't use these in motor controls. We don't use this. We have to use one of these to identify what type of timer it is. So in motor controls, the coil does not identify what timer it is. What identifies what timer it is the contacts that we use. That makes sense? So what do we need? Do we need an off delay timer or an on delay timer? Well, it says after. It says after it's been on for 10 seconds. It don't say after it's off, so it should be an on delay timer. Yeah. So it says when you look at the instructions, yeah, when you look at the instructions, it says right here, it says after the red light has been on. So the red light comes on, and then after 10 seconds, it turns off. So that right there identifies it as an on delay. If it says 10 seconds after the red light turns off, then we'll be using off delay, right? But here it says 10 seconds after the red light turns on. Oh, we'll do that. Are we okay? So if this was an on delay, what would it be? The red light should come on instantly and then turn off after 10 seconds. So we got to use an on delay. So we'd use one of these, right?
Yeah, the bigger one.
This one right here. Yeah, because we want it to energize instantly, right?
Yeah.
Okay. But what's going to happen now? This is going to close. This is going to be open. Why is this going to be open? Because this guy right here is what? This guy is true when there's no carb there. So this will work. So this is okay. This is okay. This is okay. Right? Okay. A car comes into place. When a car comes into place, it de-energizes CR. That's going to cause this guy right here to open. This guy's going to close. The timer starts timing. We're using this closed instantly. So it looks like this might work, guys, if you just use the right symbol. I don't know who this is. So the only minor problems would be, I don't know what this is for, right? And then this right here should have been a what? Yeah, normally open, not normal delay. But this one looks okay. So that wouldn't have put very much problems, right? Now, what happened? But look what they did over here. Where should these numbers be at? These numbers should be over here,
On
right?
the other side.
Yeah. And then over here, what goes over here? So over here I should have a 2. I should have a 3 with a bar under it. Then I should have a 4 with a bar. Then down here I should have a 4 with a bar, if I read that right. So over here we have numerical cross-reference numbers. Over here we have line numbers. Okay, would this one work? By the way, we have this is right. So this is good. The photoelectric sensor, some of y'all probably went back to the lab. This is a 3-wire sensor. So most of y'all did that okay. What color would this over here be? I'm waiting.
Brown.
Yeah, brown. This right here would be what?
Blue.
Blue. And this right here would be black.
Black. White.
Black.
I mean, yeah, black.
White would be a
That's really important.
if you had a single pole double throw. So here we start off. This guy's made this right here. So here he's using a normally closed. Right. So here the green. So what's wrong with this one? So this guy right here is true when there's no car. So if it's true and it's with no car, then this guy right here would be what? This guy right here would be open. So this should be a normally open. Are we okay? This one right here should be a what? Normally closed. This is a symbol for a contact controlled by relays. Somebody needs to mute their phone or what?
Mute your mic. You need to be in the house. Man, you're trying to go get in the car. No, you ain't talking about nobody. But okay.
Okay. So this shit right here should be this symbol right here. This is a relay contact. This is supposed to be a push button. I did put the symbols up there, right? For motor controls. Is everybody there?
I couldn't find it.
I put aside a brick.
Yeah, so.
What, the symbols?
Well, where you see it at? It's
There's the source content.
What's that? There's not one in handouts.
I don't know, but I found them in our other class handout, not this class.
That's okay. I got a bunch of stuff that would explain a lot. If I could see. Let me look real quick. The problem we have got handouts. Electrical control sensor sheet. Course content, handouts, electrical control sensor sheet. So it's in there. Electrical control symbol sheets. Normally open, normally closed. So yeah, it's in there, guys. So now what's wrong with this guy? First of all, I don't see a timer over here anywhere. I see a CR, I see a G, I see an R. You have a timer contact. Of course, it's a normally closed, right? So, and then we don't have anything. This guy needs to come all the way over here. So we have no timer coil over here on the left on the right hand side. Y'all see that? But it's closed.
Yeah, I see it.
Okay, what's wrong with this one?
Ain't fancy. It's not done.
Yeah, there's no timer. There's no green lights. There's no red lights.
Red light.
They have a motor starter, and there's no the whole design project does not call for a motor. All we're controlling is what? All we're controlling lights, yeah. They did not label this contact right here. This is a 3-wire sensor. They didn't put a 3-wire over there. Don't have a green light, no red light, which is the only loads that we should have out there except for CR. So this looks like somebody was just trying to get it in on time. What's wrong with this one?
No timer.
No timer, no sensor. And the name of
It looked like they tried to put a timer on that and took it out.
I don't know. I don't see. Now let's just right here what's here. There's no sensor, and the name of the class is sensors, guys. So every diagram that we're going to have is going to have a sensor symbol in there. And of course, in motor controls, that's the basic symbol, right? And the only thing that varies is between a 2-wire, 3-wire, 4-wire. So, yeah. So they got a limit switch here. There's no call for a limit switch in the whole design project. Oh yeah, I see what you said. They tried to put a timer contact here, but they have no timer coil. We just can't put contacts for timers without having a coil that controls it, right? Okay, so what's going on here? One thing they're using a PLC symbol.
That's mine. I already know. I
You're not supposed to say who it is.
I'm sorry.
It's okay. So you tell on yourself. This is the problem we have. You come directly out of what? PLCs. Yeah. So that's a instruction.
I have a hard time with this one.
Yeah.
Me too.
So we have no timer contacts. We do have the sensor that's controlling. Most of y'all picked up on using a control relay, which is good. Yeah. So somebody's going to wreck coming into this one, right? Okay, so what's wrong with this one?
They got 2 outputs.
Well, first of all, some guy's going to have to stand over here all day long and hold that push button down, or the car wash is not going to work, right? Yeah. We do have a sensor, but it's a 2-wire sensor. And this shit right here should have been drawn down because ours is a normally open, but it's true all the time. They press CR. This right here would turn a timer on. No, this guy's not going to work. You do have your lights. You do give it a tip. By the way, ours is a programmable timer. So we got 2 options. The one we used in motor controls had these 2 wires up here. The one we'll be using is kind of different. It's got a wire that comes over here, but this is okay. I'm glad you used the coil. This one looks impressive. For one thing, this is really good because the way everybody else has worked, you had no way to turn this sucker on or turn the sucker off. So here, when the person came in here, they did put a start-stop station so they could come in the morning and turn their car wash on and turn the car wash off. So that's good. Sensor looks okay. They got a run contact right here. Normally we would put a run contact probably in every one of these circuits because what would happen is that the green light would be on, right? You understand that? So that looks good. So car comes in. energizes this. The problem we have, so this is true all the time. So that means this is closed. Green light's on. Timer's off. We probably need one more contact down here on the red light. We probably need a CR contact down in here. And you don't have to put this, guys, because that comes from where? We don't have to reset relay course. So how do you set the timer on these timers? Y'all that had motor controls, you set it at the timer, right? You understand? You don't program it on these guys. You have to manually set the time. So we don't need to reset. This guy is close. It looks like it's going to be a minor problem. So what would happen? I would approve this to be wired up. Not that it's good. I'd be wired up. And normally what I do when we do this lab is I look at your drawing and make sure it has no short circuits. I'll make some suggestions. Then I let you wire it up. And then if it don't work as described, then you get to do what? You get to troubleshoot it and figure out what's wrong. But so this one looks pretty good. This one looks like I've gone over already. See this one? Okay, I think this is the last one. So what's going on here? Let's see. So this, I know who did this one. By the way, the reflector has no symbol, right? So here we start off. CR would be energized. The green light would be off. We want the green light to be on. Remember, on the retroreflective, these guys start off true to start off with. So what we need to do, if the green light needs to be on, then here we would use a normally open contact, right? You understand that? Yes or no? Okay. Then we come over here. So if this one is normally open, we want this green light to be off, then this right here would be a normally closed, right? Oh, let's see. I have to figure this out. So you got CR2 controlling this guy. I'd have to come back and look. Somebody's using 2 control relays, which is fine because according to the specs, it says you can add any additional circuit to it, right? A control device. So I'd have to come back and look at this. So that should have been closed. Push to test. Might have worked. No, unless this timer was here. This is good. CR2 closes that, turns the red light off. I'd have to look at this, guys, a little longer. But I would let whoever this is, I would let y'all wire it up and see if it worked. Oh, this was originally this one, but somebody tried to put the retroreflector in there. So that was all the ones that had been turned in. So like I said, so this is a repeat. So that was 1, 2, 3, 4, 5, 6, 7, 8. We had nine attempts out of 16. So we had 7 people. I gave y'all a second chance, guys. I sent a text out last night. If you're on the list, I have two students that when I sent the text out, undoubtedly they did not respond to it. So there's 2 students in the class that are not going to get text from me. I'll post the information on the Blackboard so y'all can sign up yourself because I can't sign you up now. And if you want to get text, and text is the best way to do this because I know y'all not going in all day long and checking your college email.
I got a problem with my email. I can't log into it.
So you definitely need to get text. And by the way, I think James Roy did that. For these projects, if you're having problems with your email, it looks like you can attach things to messages. So I'll do that. What you need to do if you got text, just send me a text saying, I submitted it through message, because one of the students, one of y'all did that where y'all actually attached it to, you can actually attach this stuff to the message. So that's a good point too, because some of y'all, if y'all having problems with email, but you can get on the Blackboard Ultra, message allows y'all to attach files to that too. So these turned out pretty good, guys. I'm glad y'all made these attempts. It looks like taking the pictures. That's a really good picture. It looks like taking the picture and then submitting it. Looks like that process will work when we do any more design projects during the term. Okay, guys, let's take a 15-minute break, and let's see if I can bring up my other stuff, okay? Okay, guys. Can y'all hear? Can y'all see my screen?
Yes.
Okay. Interesting conversation, guys. All right, so I wanted to go back and show y'all some stuff that I wasn't able to show y'all the other day because I didn't have them here with me. This is a reed switch, a dry reed switch. And so this is actually a reed switch right here. And you can almost see the contacts. And what does this guy sense? Magnetic field, right? So here's a magnet. And you can see my ohm meter. What I'm going to do is just bring this close to it. And can you see what it's doing? Now it's got to, doesn't work this way. So what you got to do is you got to have a north-south pole. And all I'm doing is bringing the magnet up close to it. Can y'all see it?
Yeah.
Okay. So this is a magnetic. This is a reed switch, and it detects a magnetic field. This will be a two wire sensor because it does not require power to operate, because all it is just basically a contact that's controlled by a magnet. So what we do is we mount the reed switch in a stationary position, and then we take our magnet and mount it on whatever's in motion. Oops, sorry. We mount it on whatever's in motion. And then when it's at a proximity at a certain location, then this guy here would let us know. Okay. This is very cheap. It's used a lot of different places. Comes in a lot of different sizes. We can actually wrap a coil around the reed switch and put DC through it, and we can actually trigger. So a lot of the relays that's used on PLCs, these are actually just nothing but reed relays is what they call them. So all it is just a combination of a reed switch with a coil of wire wrapped around it. And I'll try to do that and see if we can get to that next class. I think all the rest of them we were able to look at, right? I showed y'all Hall effect on the printed circuit board. And we looked at so what does capacitive sensors do? Yeah, capacitive sensors can be designed to sense almost anything, right, guys? So, I mean, that'll sense me. Then we have inductive sensors. What do inductive sensors sense? Yeah, metals, right? So, like I said, you run into these all over the place. So, and then we looked at light sensors. And I've got some of those available to us. Oops. Oh, crap. So this is a photoresistor. And we run into these a lot of places. These are basically what's turning on our street lights now. Now these guys right here can't handle the power of a street light, but it can definitely bring in another device that can control the street light. This guy right here is called a photoresistor, so what do you think it varies? Called a photoresistor. Huh?
What's the question you think?
Yeah, so this guy's a photoresistor, so what do you think it varies? Changes its resistance with light. Yeah, so you see I put my shadow over it. Can you see what happens? The resistance goes up. If I take my finger away, the resistance goes down. Yeah. So, of course, the more light we put on it, the less resistance it'll have, right? So this is the sensor that's on all our street lights now, that turn them on at night and turn them off in the daylight. If you got motion detectors or any type of lights on your house that does this, that come on at night, then this is the actual guy that's actually sensing the light. This is actually a semiconductor material that they run in here. So. I don't have a photodiode, but I do have a phototransistor. Let's see if we got these guys in here. Some of my stuff is missing, so I don't know what's going on, guys. This is a photodiode. So what we need to do is we need to.
I can't see anything. What is it?
Video down. Hold on, for the darker. Y'all believe it's flowing the clock on out there.
So y'all can y'all see my PowerPoint?
No, sir.
Okay, sorry, it disconnected me. So this is a symbol for a photodiode. So do y'all know how a check valve works? So how does it work? Yeah, it only lets a fluid flow in one direction. Well, this is the same thing we have with these guys. These are called diodes. Yeah, and a diode only lets current flow in one direction. So we have, in solid state, we have something called bias. Bias is a DC voltage that we apply to a semiconductor. That controls its operation characteristics. So we have two leads. This guy that's got the bar We call this the cathode. And this came from vacuum tubes. The arrowhead, this is referred to as the anode. Now to forward bias a diode, what we have to do is we have to make the cathode negative in respect to the anode. And then this guy here will turn on, it'll let current flow. If we come over here and reverse the polarities, then what this will do, this will block it, but there is a path through there. So this is not like this, we say when it's forward bias, it acts like a closed switch, and when it's reverse bias, it acts like an open switch. But it's not an open switch. There is a path through here. So what happens is we have a really, really small current flow through here that we refer to as leakage current. Now what controls the leakage current, number one, is the temperature. So the higher the temperature, the more leakage current we have. And this is why most of your solid state or your semiconductor devices are susceptible to heat. So that's why if you ever get around like a robot or something or a computer, you'll see blowing fans blowing across these semiconductors to try to limit the leakage current. Another thing that we can do that can increase the leakage current is if we expose the actual semiconductor diode itself, if we expose it to light, then what it'll do, the leakage current will come on. So what we do with a photodiode is we put it in the circuit reverse biased. So over here we're going to put a what? A plus. And then when we expose this to light, the more light we expose it to, the more leakage current it lets through. And the less light we expose it to, the more leakage current it lets. Did I say it right? The more light we expose it through, the leakage current goes up. The less light we expose it to, the leakage current goes down. So these guys, so the disadvantage of a photoresistor is that it's got a slow response. So these guys work okay like on street lights because it goes from night to day very gradually, right? So this is the biggest disadvantage of a photoresistor. By the way, a lot of people call these things photocells. So the commercial name is photocells. The technical name is a photoresistor. And this is the way you would buy them. Here's the symbol. This is the ANSI symbol. And then this right here is the IEC symbol. Y'all know what those are? Anybody know what these stand for? Yeah. This is American National Standard Institute. So a lot of your drawings over here are going to be done like this. But the problem is now we have a lot of countries that's in here. So odds are they'll use this symbol right here. This is I know this is a European Council. I can't remember what the I stands for. But this is the standard that most of y'all are going to see since y'all work for companies, you know, that their home headquarters in another country. But the biggest problem we have with these guys is they're what? Slow. These guys right here are fast. These are semiconductors. These guys are extremely fast. In fact, photodiodes are probably the fastest light sensor that we have out there. The only problem is...
Hold on, Rich, go back to the slide.
Which one? This one?
Yeah, hold on.
Let me look up Let me look up IEC real quick. That's something I should know. I had it on my other slide, but I can't get to them.
Alexa, what does IEC stand for?
International Electrotechnical Commission. So I got the European wrong. Electrotechnical Commission. This is an international standard. So over here in the U.S., you'll see a lot of these ANSI symbols, but you'll also see a bunch of these because these are international symbols. So if I use these symbols right here, then people in another country might have problems with them, even though probably not, but these are both. But the telltale sign is these arrows pointing in, right? Can y'all see those? So anytime we see these two arrows, it means they're light sensitive. So when I came over here and drew the photodiode a while ago, these are supposed to be, then I came over here and put these two arrows, which means these guys detect light. If we come over here and do this, and then we draw them going out, then what does that mean? These guys emit light, right? So these are your LEDs. And what does LED stand for? Anybody know?
Light emitting diode.
Yeah, light emitting diode. So if you see the two, if you see the arrows pointing in, it means these guys detect light. If you see it pointing out, then it means these guys emit light, right? That makes sense? And most y'all see we have LEDs all over the place. In fact, most of our LCD screens now are backlit with LEDs. Originally, they was backlit by a big old fluorescent light. And the problem with that, if you lost that fluorescent light, so we've got about 10 monitors up in H111, that all of them's bad because the fluorescent light bulb went out in the back. If you've got thousands of LEDs lighting the back of your LCD screen, then if one little diode goes out, it's not going to cause you any problems, right? So what we do with this guy is we come over here and we put this guy in the circuit reverse biased. So we put the plus over here. Now the problem is these things here work off leakage current. So that means these guys cannot drive loads. So we'd have to bring this guy over here and we'd have to hook it up to some big old amplifier. Before we... Huh? Go ahead.
Now you said the more light, the leakage current goes down?
No, I said that and then I corrected myself. I said the more light, the leakage current goes up. The less light, the leakage current goes down.
Okay.
Oops. And so the biggest problem with these guys is we can't run loads with them. So right off the bat, we're going to have to amplify them a lot. So usually we use operational amplifiers, and I think I got a circuit at the end of this PowerPoint that I can show you. But those are our check valves, guys. These are the guys that turn AC into DC. But these photodiodes depend on that leakage current. Are we okay? Yes? No? Any questions? Okay, so everybody understand what bias is. Somebody said, As soon as I get my marker up, guys. Sorry. So what is bias in semiconductors? This is a DC voltage that we apply to a semiconductor to control its operation or conduction characteristics. Conduction would probably be a better word. So this is one of the main uses in solid state of resistors. Because when in DC, what kind of work did your resistors do in DC? What kind of power? What was their power? What kind of power did they release? They released what? They heat. That's all they did. That's all the work they did. So all you do when you have a electric heater, all it is a resistor. I dropped something, guys, and I can't find it. That's okay. We'll use the picture. So this is not a photodiode. This is a photodiode. So notice it's got how many leads? 2 leads. This is actually a device called a phototransistor. Anybody had solid state? So what is it? So this is the basic symbol of a what we call a bipolar junction transistor. A lot of people call them just BJTs. And this guy's got 3 leads. We call this guy right here the emitter. We call this a collector. And then this right here is called the base. So what do we do with water? What do we do with water valves? So what do we do with water valves? We control the flow of water, right? Now what happens if you got this thing turned wide open and you try to put your hand under here and try to stop this? What's going to happen? You're going to get wet, right? Okay. So you cannot control the flow of the water valve with your hand. But what we do is we get a mechanical advantage with these things up here. Even though that thing's really small, it's got a screw thread in here that acts like an incline that gives us a mechanical advantage. So what we can do is we can precisely control the flow of that water with that valve. Well, all the transistor guys, this is a current valve. So if you understand how a water valve works, then you can understand what a transistor does. Here's the actual flow. Here's the actual valve itself. So the main valve is between the collector and the emitter. And this is your... We're there? Yeah. And this is the knob right here. So what we do is we put a real small current into the base to control a lot of current between the collector and the emitter. We can operate this thing as a switch, or we can operate it as what we call the linear region. This is where all your amplifiers operate. So here we're going to operate it as a switch. So what it does, it takes a really small current here to control a lot of current here. But what we're doing now is we're providing that energy with light. So this is the symbol for a phototransistor. So this is a symbol that we do. Another symbol you might see is just this with two arrows pointing in. Now, what advantage does this have over? This guy doesn't operate as fast as a photodiode, but what advantage does this guy have over a photodiode? This is the primary thing we use, guys, right here. It's the sense light. We use phototransistors. So what do you think the primary advantage of these guys are? Nobody knows?
I'm sorry, what was the question?
Yeah, what would be the primary advantage of a phototransistor over a photodiode? They both sense light.
The intensity of the light it receives?
Well, it works the same way. So the more light I put on this thing, the more current we get from between this right here, right? Over here, though, this guy right here is going to be dealing with probably picoamps. This guy over here, we can get them to control amps, but most of these guys control milliamps. So the advantage of a phototransistor is we can control a lot more current with it than we can with a photodiode. So we could actually run a load with this if it worked in the milliamp range, or we could amplify it really, really easy. So the biggest advantage of this guy is that this guy can control about 1,000 times more current than a photodiode. So this is the primary device right here, guys. They can be designed to sense visible light or visible light, VIS, or it can sense infrared. So a lot of our light sensors that we use, like to control our cable box or to control our Roku or whatever you have, these guys use infrared. So that's why you can't actually see them flashing, right? Control your DVD player. So the big advantage of a phototransistor is that we can control a lot more current than a photoresistor. I mean, I'm not a photoresistor, excuse me, a photodiode. So photodiodes, you don't see them much anymore. I could probably go up to where we order our parts from, and we order a lot of parts from a company called Jamico Electronics. And then we'll just search for photodiodes and see how many of those they sell. And we'll look at phototransistors and what we'll do. And we'll look at the price also. So the primary device in our photo cells are retroreflectives, are diffused, and also are through the beam. That the actual receiver element itself is a it's probably a phototransistor. I would imagine. So are these analog or digital devices?
Analog?
They are analog. You're exactly right, but we can convert them into digital pretty easy, right? By bringing it through a threshold detector like we talked about on ours. So a lot of our sensors actually use an analog device. So up here we might have the phototransistor. And then this right here would go into a threshold detector. And this right here might be variable, guys. So some of them are actually variable, right? And then we'll get a digital output out. So all the digital photo detectors, the through the beam, the retroreflective, and the diffused, all these probably use photo transistors as the detecting element, and then we run it through a threshold circuit, and we get a digital output. Are we okay? This is a photovoltaic cell. Most people call it a solar cell. So the commercial name is a solar cell. The I can't find my goodie box. It's got my parts in it. Okay, guys, y'all take another 15-minute break and remember your bit. Yeah, watch your language, right? Okay. Are we okay? Huh? What?
Don't forget to pause.
Yeah, I'm on pause. Can y'all see? I'm on pause. Okay, guys, this is what we call technically it's called a photovoltaic cell, but this is what most people commercially known as a solar cell. And what do these guys do? Anybody know? So these guys right here actually absorb the energy from light and convert it into a voltage. So this is a photovoltaic cell. This is a small one. And of course, what we can do, we can treat them like batteries. So if I hook batteries in series, what does that do? Anybody out there? So basically the symbol for this I think I lost. Can y'all see the white screen? Whiteboard. So if we hook batteries in series, we call this series aiding, what do we get? So if this is 3 volts and this is 3 volts, and I measured across here, so if we hook batteries in series, what do we get?
Hey, Rich, I couldn't hear anything you just said.
If we hook, can you hear me? Can you hear me now? Yeah, my microphone kicked off. So if we hook batteries in series, yeah, I can't. It won't share my screen right now. I can't share my screen. I can't share the PowerPoints. Y'all see a PowerPoint up there?
No, all we see is the 3 volts per series.
Y'all see the whiteboard though, right? So if we hook batteries in series or DC sources in series, what does it do? Yeah, they add, right? If we hook them in parallel, so what adds? So I'll come up here and hook them in parallel. Now these have to be the same voltage level. But what do we get when we hook DC sources? These are actually the symbol. A lot of people say they're the symbol of a battery, but technically this is a symbol that's been adopted for a DC source. This pen don't work too good. Okay, so
Is it me or is it your internet lag?
I don't know. Like I said. So up here I have 2 3-volt batteries. Can y'all see them? They're hooked in series. We call this series aiding. Down here I have 2 that's hooked in parallel. So what's the difference between hooking them in series and what's the advantage of hooking DC sources in parallel? Nobody knows?
Increase voltage and in parallel increase the current.
Yeah. So here, that's good. So here we increase the voltage. And this drawing don't work too good. Over here, we're going to increase I. So when you look at your remotes for your TVs, some of the time they're hooked in parallel, sometimes they're hooked in series. What advantage does a higher voltage have over a lower voltage? So what advantage does a higher what advantage does high voltage have over low voltage? Nobody out there knows? Nobody knows?
The advantage that high voltage has over low voltage?
Yeah, the higher the voltage. What advantage does a higher voltage have over a lower voltage?
Somebody answered that.
Who did? I didn't hear anybody.
What?
So what are we trying to provide? What am I trying to provide? What type of work are we doing? What in electronics and electricity, what type of work are we doing? What's that unit? No. So this is what you pay. This is what you pay every month. You don't pay for current. You don't pay for voltage. You pay for, what's that bill you pay for every month? You call it the what? Power bill. So the big problem is that if power is equal to, what's the formula? Power is equal, the main formula? Yeah, V times I. Yeah, or I times V. So what would I be equal to? If I rearrange this formula, if I say power is equal to V times I, it's equal to P divided by V. So I'm trying to sell you power. Alabama Power, they're trying to sell you power. But they're trying to get that power to your house, right? You understand? And of course, they're trying to get it through conductors. What determines the resistance of a conductor? What determines the R of a conductor? Yes. Somebody said no. We're just trying to see what determines it. What determines you? So somebody said length. That's good. What's the second thing that determines it? The what? Or the material? I don't know if that's what you meant, but that's what it is. What's the third thing? Starts with a T. Temperature. In fact, when we get to temperature sensors, we're going to talk about a guy called an RDT, which is a resistive temperature device, which is going to measure temperature because what's one of the things that controls R? Temperature. Okay. So what we're dealing with when Alabama Power is trying to sell you power, they're trying to sell you power, right? They got two options to this. They can change the voltage. So what advantage does a high voltage have over here if I'm trying to sell you power? So I'm trying to sell you power. Let's say I'm trying to sell you 1,000 watts of power, and I do it at 10 volts. What would the current be?
100 amps.
It'd be a 100 amps. I'm trying to put that 100 amps through a conductor, and the conductor has an R. Voltage drop is equal to what? V times R, right? I'm sorry. Voltage drop is equal to V times I. So the problem is this higher this I is, the more voltage that the conductors are going to drop. If I come over here and I provide you that 1,000 watts, if I provide that 1,000 watts at 1,000 volts, what would my current be? 1 amp. So that means if I was using the same gauge wire, the 1,000 amp would drop a lot more voltage than the 1 amp. So what happens, the higher the voltage, the smaller our conductors can be, right? You understand? And if you look at some of these remotes and you tear them apart, they are nothing. You know, the wires over there are very thin. So that's why we instead of using a 1.5 volt battery, we use we use 2 of them in series or 4 of them in series. Flashlights do what? So flashlights usually have at least 2 batteries in them, right? I've seen flashlights that had 5, 6 batteries in them. So what we can do is we can do one of two things. We can get more voltage at a watt at a lower current to get the power. Are you okay? Everybody understand that? So if we hook these batteries in series, what that means is we can use smaller conductors. We can have smaller devices. So if we have the higher the voltage. So this was when Alabama Power sends you. So if Alabama Power transmitted at 750,000 volts, they could send 1 watt. They could send 750,000 watts of power with 1 amp of current. Which means what now? What can they do? Well, they now, instead of using copper, they can use what? Aluminum. And of course, what advantage does aluminum have over copper?
Cheaper.
Yeah, it's a lot cheaper. So these solar cells, the solar cells themselves are fairly small. But when you start looking at these solar panels, these are just a bunch of solar cells that they're hooked in series to get the voltage up. and they're hooked in parallel, then but they're series parallel, right? So a solar panel might look like something with this. It might have 1,000 of these inside there. So a lot of them, it's going to hook in series to get the voltage up. Then they'll hook a set of series in parallel to get the current up. And anybody know the symbol for a solar cell? Nobody knows?
I'm gonna say no.
So they do a.
What you were drawing on this whiteboard, and I've been leaving and coming back. I don't know what it is, but I've logged out and logged back in.
Okay. So that's a symbol for a solar cell right there.
I think he's lagging too.
Yeah, I can't. Can y'all see the symbol?
I don't know. Can you check your connection over there, Rick?
Yeah, I've
They look good on my side, Rick.
Okay, see if this is it better? Is it better now?
Yeah, it's a lot better.
I lost my wired connection. My wired connection came unplugged.
Well, y'all been on y'all laptop.
What you doing with it, Rick?
It said it is better.
The speed.
That's what it says.
Yep, that's what you just typed.
Yeah, should be updating faster, a lot faster now. My wired connection came loose, and I was on my Wi-Fi.
I see the screw scrap over there.
You see this? You see the actual symbol, Sancho? You there?
I see the circle that they just put the.
But there's nothing in there?
No.
Okay, so this is the symbol for a solar cell, or a photovoltaic cell.
Okay.
Okay.
I see it. It looks real good.
Yeah.
So, don't mind it off. You know, yeah.
Wait, hold on. Uh-oh.
If I got clothes on. So this is my meter. Can everybody see my meter?
Yes, sir.
Okay, here's a photovoltaic cell. And what I'm gonna do is I'm gonna take my meter and hook it up. If I can find my leads. This is supposed to be positive. And then this right here is supposed to be negative. And I need to put my meter on volts. And it's kind of dark in here while I'm recording, guys. So we got volts DC.
I see you clearly. I know what you see. I see you good, Red.
So right now this solar cell is putting out around 33, 34 millivolts. Then I'll take my flashlight and shine on it. And now it's about 330, 40, 50. So what this guy is actually doing for us, it actually produces a voltage that is proportional to light. So what would be the advantage of this? So is this going to require an external power source? Photoresistors. Yes or no?
No.
Okay, so these guys change a resistance proportional to light. How am I going to get this into a control system? Because one thing that we cannot transmit. What's the one? We got three things we can send. Our sensors can send out a what? They can provide a voltage, or they can provide a what? They can provide a current. That's the only thing I can send through through conductors. I cannot send a resistance. So if I wanted to use this thing, one way we could do it, we could use it in a Wheatstone bridge, or we could come over here and do this. And then I could come up here, let's say I make this 24 volts, and I make this 0. And then I'm going to do is I'm going to take my output right here. Right now we'll hook up a voltmeter. So a photoresistor, for it to do any good for us at all, it's got to have an external power source. Because what does it do? It varies its resistance. So what would happen here to my voltage when I put light on it? Would it go up or go down? When we expose this to light, what would my voltage be? Well, when light goes... So somebody's echoing. When this thing right here, okay, when this guy right here, when light strikes it, its resistance goes down. If its resistance goes down, then the voltage over here is going to do what? It's going to go down. So here the voltage would vary in the same direction as the light. So as the light goes up, the voltage goes down. My voltmeter would show. If we wanted it to go the other way, if I wanted it to go the opposite way, the way y'all were talking, I would come up here and I would put my sensor up here. And then I would put a fixed resistor. Now this would be my light sensor. So here, if the light went up, if the light intensity went up, this resistance would go down and the voltage drop would go down. So if I take my output across here. But this guy right here has to be powered. Okay. Does this guy... Oops. Does this guy have to be powered for it to work? course, here's our photodiode. Here's a symbol. Symbols are going to be on the test, by the way. You're supposed to color it in. Then I come over here and I draw the two things come pointing toward it. Two arrows pointing toward it. Does this guy right here have to be powered before it works? Yes or no? You're exactly right. These guys have to be biased. And what is bias? A DC voltage applied to a semiconductor to control its conduction characteristics, right? So every semiconductor, these guys have to be powered. Does this guy have to be powered? The phototransistor. For it to work? Yes. Because does this guy have to be powered before it works? No, you're right. So this guy right here produces its power, right? You understand? So this is one advantage of a photovoltaic sensor is that it can produce the power without us running power wires out there. So this is one big advantage of this. Of course, we run into these all over the place. Like on street signs out in the middle of nowhere on the interstate. You'll see a box over there that's got solar cells pointing up in the air. We have California, I think, has got a big solar panel array out there that they're producing. Now, you got to understand, these guys produce what type of current? Direct or alternating?
What kind of car?
Current. What type of current? What type of, that's your car. Yeah, these guys produce DC. Okay. These guys work off DC. These guys work off DC. This guy's nothing but a resistor. So this guy don't care if this is 24 volts DC. He don't care if it's 24 volts AC. It would work the same. So one little advantage we have on a photoresistor is that we can power it with AC or DC. A photodiode, we have to power it with DC, and then of course phototransistors are DC. These guys right there produce their own DC power. So these are photodetectors, guys. These are the actual sensors. So we looked at some proximity sensors, but what we have to understand is these through the beam. What we have to do is we have to have a light source, or a transmitter. And over here, we're going to have a receiver. And this guy's got to have some type of sensing element. So what is this sensing element? It could be a photoresistor. What's the biggest disadvantage of a photoresistor? I'm listening.
Reaction time.
Yeah, it's slow. Could be a photodiode. What's the disadvantage of a photodiode? Anybody got the answer?
The density of the light.
The vantage point?
What's that? I'm listening. These guys, the biggest the problem we have with the photodiodes is they're very low current capabilities. In fact, we said it was in the picoamp range, right? Phototransistors, these are mainly the ones that we use inside our photodetectors, are through the beam as the sensing element. Through the beam, also retroreflective, and also diffused. Odds are the actual sensor itself, in the sensing element inside the sensing head is probably a phototransistor. Are we okay? Questions on light sensors? These are actually the sensing elements. So we actually looked at what would be inside a photo sensor that actually senses the light. Of course, most popular, of course, is a photo transistor. This is probably what's in your TV or your cable box when you use your remote control. It's probably got a photo transistor in there as a sensing element. So photo transistors now are by far the most widely used. The biggest advantage of a photoresistor is their speed. So of all the light sensing elements that we looked at, the photodiode has the fastest switching speed. So if I need extremely high, fast switching speeds, I'll probably use a phototransistor. A photodiode. Are we okay?